Hello. In this video, I'm going to be showing you how to simulate airflow over some large terrain from a height-map.stl file using OpenFOAM. Just a disclaimer, this tutorial is best if you're already familiar with the basics of OpenFOAM simulation, so I recommend familiarizing yourself with the program before watching this video. Okay, so I'm going to start off by explaining what files you'll need in your folder for OpenFOAM. You will need your zeros constant system. In your constant file folder, you're going to have a folder called triSurface, spelled exactly like this. You'll also have a polyMesh folder, but it's going to be empty because you haven't run your blockMesh yet, or your snappyHexMesh file. But in the triSurface folder, you should have your STL file just sitting right in there. Mine is like a 512 meter by 512 meter square with like terrain sticking up out of it, which is what I assume most people's terrain will probably look like. In the system folder, you should see, at least for this step, you should definitely have blockMeshDict and snappyHexMesh. For both of these, you're going to have to, so for your snappyHexMesh, let me have this open already in files. You're going to see, this is what will convert your STL into like the mesh. So you're going to want to, if you want, you can add layers. You don't have to do that. That's if you just want it to look nicer. So you can see, you'll see your file name right into there under geometry, and you can name it. I'm going to have all of this posted in the description of the video, so if you want to just rename your STL file to terrain.stl, then you can even reuse all of this without having to change anything. In the mesh controls, this will control the maximum size of the mesh, because you don't want it to become crazy huge, even though these numbers are pretty large. It's just to make sure that it doesn't get any larger than this if it's trying to overmesh it. In features, you might be able to like refine some surfaces. That'll just smooth it down so that you don't come across errors later when it's trying to cut out a section from the block mesh. And all of this. One thing that's interesting here is I put the scale at 5.12 because even though I wanted it to be 512 by 512 meters, the file somehow came out as 100 by 100 meters, so I've just multiplied it by 512 or 5.12 to make it 512 meters. That makes it so it will be the size that I expected it to be. I didn't notice, so yeah, you'll see this. All of these, most of these can be changed slightly if you want to see something different. This is pretty important though if you want to make sure that the terrain shows up as a wall type. That way it'll be interacted with in the same way that a wall would be in a typical simulation, which is good for terrain. Refinement regions, if you want, you don't have to do that. Snap controls, add layers controls, and then some advanced settings where you can like change. These are just to change around to make some stuff a little bit smoother. Again, this whole file will be in the description inside of Drive, so you will be able to play around with most of these numbers yourself if you want to. And that should be everything in snappyHexMesh. Now, the concept here is that you're going to make a large block mesh, which will just be a giant rectangular prism, and you're going to have the vertices. I put mine at, basically it spans from -400, -500, 0, all the way to 1200, 500, 300. 300 is the height that I chose. The maximum height in the terrain is about 40, so I just decided to go pretty tall to make sure that the terrain did not have any interference with the top surface, because again, you have a bounds that you're working with, which I will show off in this section after I run the block mesh. But you will, depending on the size of your terrain, I would say make the width roughly double the width of your terrain. Give yourself a little bit of headway. This is This is about 175 meters of headway, I believe. I know that my model goes backwards by about 250. So yeah, this is 150 meters of headway. And then after the terrain, give it as much length as you think it might need, because the wind will be affected for a long ways after upwind of the terrain. For the boundaries, I gave an inlet, outlet, sides, top, bottom. For the sides, I chose a symmetry type because it just kind of makes everything a little bit smoother. You don't have to worry about anything crazy happening. And yes, that's everything for the block mesh. I'd say make sure the block is substantially large. I'd also check make sure that your mesh for the STL file is not like raised up any amount, because if it is raised up or something, or at a weird coordinate, I would affect these coordinates as the mesh's coordinates are affected. That should be all for this section. What the next thing you're going to want to do is you're going to want to run two commands. First, you're going to run blockMesh, and then once you run that, you're going to run snappyHexMesh-overwrite. That last little bit is just to what that's going to do is it's going to, once you create your block, the overwrite snappyHexMesh is going to cut that terrain out of your block. So you're simulating in the block, but the terrain is cut out of it, so it's like the terrain is right there with it. Just making sure that I got that spelling all right. Nope, I didn't get that right. Overwrite is all lowercase. Okay, snappyHexMesh overwrite, and that will conclude this section. In the next section, I will show what to do with the results. All right, so after running blockMesh and snappyHexMesh, you will find yourself. This is because I made a copy before running, and this is the copy. I've named it Terrain Tutorial After Mesh. You will see that you've now created the terrain object files. In your constant triSurface, you will see VTK file has been added to that. And in the polyMesh, you will see that the polyMesh folder is now full of your mesh details. This should all be expected. This is just like a sanity check to make sure that you to make sure that you have everything that is expected after blockMesh and snappyHexMesh. So now I'm going to show off what I've got in ParaView by running paraFoam. This is just if you want to check out what happened in the tutorial, or this is just to see if it all came up correctly. Here we go. All right, so here's ParaView. In my case, I would say the internal mesh, you might not want to see all this stuff. Bottom wall, sure. Inlet patch, outlet patch. These are all just the walls that are, this would be like the entire cube if I were to render all of those parts. But let's see, I'll hit apply. Oh shoot, this might crash. I forgot to say that P and U are not defined yet. Well, so long as you don't select P and U yet, because I accidentally left them selected in the fields, but they don't really exist yet, so this is fine. So here you can see the terrain sticking out of this. This is the bottom face, this is the terrain face. And you can see that I've made the terrain a little bit, the terrain that I input was low mesh, or low resolution mesh, and what I've accidentally input is something a little bit higher than that. So I'm gonna switch to 2D viewing so that I can get a better look at this. This just makes it easier to click drag sideways. So you can kind of see that the mesh that it generated is, a bit higher quality than the mesh that was put into it. So there's like all these like little cuts and things, even though you can still kind of see the triangular faces that made up the original low quality mesh. That's just because I didn't think that I would I didn't think I would make it resolve that fine, but this does go to show that if you have a really high resolution STL file, it will still have no problem, you know, coming up with really high resolution detail, at least relatively. And you may notice that the terrain, there used to be a little more terrain around this area that was really low to the ground, didn't have very high elevation. And because of the way that I set up my file, it kind of cut that out, because really there's no meaningful height difference between the flat layer and like the hills. So the only things that really came up was the extreme hills that popped up in the original STL file. These are like the mountain regions and stuff. But what this really is this is a cutout of the full block. So what's really been generated is a block, and then this is all cut out of it. So let me render the whole block. It'll look kind of stupid at first, but all right, here we go. Switch back to 3D. Can I zoom out? Yes, I can. It's a little bit laggy because it's rendering, so oh, that's probably why. It's rendering a lot of detail, but there we go. You can kind of see that the terrain is like cut out of the bottom of the block. So if you were to, let's say, build in a cut face, let's make this aligned with, you know what, that's a fine axis. Let's do that. If you were to make this cut here, there we go. It's taking a little bit of time because it's running both the screen recorder and the it's running both the screen recorder and that. But yeah, all right. So here's the cut out of the face. Ooh, boy. Let me look at the normal thing, please. There we go. So you can see, like, even if you make a cut, you can see the terrain is sticking into it here. And it's like a hole that's been punched into the bottom of the box so that the air inside the box that's being modeled will be flowing properly. And it will bounce off the top of this just like air would impact against a real-life mountain or something. But yeah, that's it for the mesh section. Just checking this to show that it does all work and it's all in here. So yeah, on to the next section. I'll explain how to run the actual simulation. This took me like 40 minutes to run the actual simulation, so I'm just going to show you the commands that you're going to run and then go into and then I'm going to switch files to the completed simulation. Alright, so now I'm going to show you what you'll need before you run the actual simulations stuff. So now that your block mesh has been made, I'm still in the after mesh folder. You're going to want to make sure that in your system, if you're working with something really high detailed like what I was working with, I would recommend having the decomposePar. Because that will basically split your simulation into 4 groups, which makes it run about 2 to 3 times faster than normal. It's not an exact like 4 times as fast because there's a 4-way split, but it makes it run in a reasonable time. My simulation was going to take me like 2.5 hours or something stupid, and I changed it back and reran the simulation with this, and it took me only about 45 to 50 minutes, which I definitely appreciated, not having to wait 2 hours to see if my mesh even like properly simulated and worked. In Schemes and Solution, you'll see these files typically are the same for most simulations. my solution file. Let me open you up. You can see that I've chosen the solver to be the K epsilon kind of solver. So it's most of this is reused from one of the tutorial files, Pits Daily, I believe it's called. But yeah, this is going to be, all of these files will be in the description inside of the drive folder. Elsewhere in the system, you will see controlDict. That will just control the how fine the results are. In the 0, you're going to want to make sure that your inputs, so for example, the only thing I'm really inputting into this is a velocity of 10 meters per second. So, hold on. All right, here it is. I've put in a velocity of about 10 meters per second in the X direction, which is blowing across the terrain. So it's just, traveling right across, impacting the mountains, which you'll be able to see pretty good visualizations of that once I've run the simulation. So on the inlet, I've put in that internal field, which is like all the air in the simulation. I've also made it be going at 10 miles per hour, or no, 10 meters per second, sorry. On the outlet, it's just 0 gradient, terrain, bottom, sides, top. You're going to want to make sure that in all of these you include the terrain as its own section. Usually give it the same thing as the bottom face has. So in the case of velocity, I put no slip condition because I'm assuming very little friction from the terrain, but there should realistically be friction, and there are ways of adding friction to surfaces, but I've just put it as a no slip condition. So, oh wait, no, hold on. No slip is friction. There is a small amount of friction. Slip condition is what I was thinking about. On the top of the simulation, way up in the high atmosphere, that's where I put the slip condition, where there's just no friction at all. So yeah, 10 meters per second input. And then the other files all will have very similar boundary conditions labeled with the same group of boundary conditions that you'll need. And if you're running a K omega simulation, you're going to just change this from epsilon to omega, change the input files to match that. Or not input files, the internals of this file, you're going to want to match it. So you'll see that for epsilon, it uses epsilon wall function for the terrain, epsilon wall function for the bottom. And for the sides, I also keep the symmetry, 0 gradient, and at the inlet, I've given it just a small fixed value, which is just to, and it's same with the internal field. There's just a small fixed value all across the entire thing, wherever the velocity of the air is going. But at this point, you should be clear to run 3 commands. Now, I'll warn you, it took me, again, 45-50 minutes to run it all. So I would be aware that this might take a very long time. Here, close that. So the first thing you're going to want to run is definitely the decomposePar command, which looks like this. Compose_par. That will split it all up. I'm not going to run it right now because I don't want to change this file before uploading. The next one, which is a little more complicated to run, this is going to actually run simpleFoam, but with the 4 different processors. And this command looks like mpi run, one word, space, dash, np, which I assume is number of processors, 4. And then you're going to do simpleFoam, and then you're going to do parallel. Did I spell parallel correct? Yes, I did. That should be the full command. You're going to run that, and that is going to take like 45-50 minutes, but it's a lot better than if you didn't use the decomposePar command, because in that, if you don't use the decomposePar, it's going to run it all with like one processor, so it's going to take really a long time. But after that's done, you're going to quickly do reconstructPar. Did I spell that right? Yes, I've spelled that right. And that will reconstruct it. That shouldn't take long. That took me like probably about a minute. And then after that, to view it, you're going to again type in paraFoam to view your results. Now this isn't my results folder. In fact, I'm gonna show my results folder after this quick transition. Alright, so after running that simulation, which should take like I said, 50 minutes, 45 to 50 minutes, you'll notice that all of the time constants, which are all inputted into controlDict, will have all of the, because I put 50 as the time interval, so every 50 seconds it gives me a new one. And then at 500, that's when I put my end time. You'll notice that there are now 4 processor files. And that is really all that you should notice different here after it's been solved. But yeah, now I'm going to show you the ParaView model. All right, so here I have opened the file in ParaView, and you can see the results. Right now I've got pressure on, so I'm going to quickly play through the time you're going to see change here, and I'm going to play through all of the pressures. Looks a little messy right now. That's unexpected. Why is it doing that? All right, let's switch back to U and then go back to P. Maybe it'll be smoother. That's more expected. I don't know why it was doing that. But you'll see here that it's looking really fine. You can see the results. You expect the high pressure to be, again, the wind's blowing from here to here. So you can expect high pressure right at the bases of these ridges and mountains, where the pressure just increases as it hits, but then right as it starts to cusp past the peak. Low pressure points, like right at the peaks of the mountains, where you'd expect it. You know, if you've ever been on top of a mountain, you'll expect like the pressure gets low, especially because the wind's blowing faster in that location. In fact, you can't see velocity in this mode, because you'll notice the, well, I'll just show you. The velocity is like 0 at the ground. Like this is just the exact face. So right at the ground, it's all 0 velocity. But if I were to switch to epsilon, let's go back to velocity. And instead of doing that, I'm going to zoom out, rotate this up a little bit, and I'm going to remesh to include the internal mesh here. I'm going to apply the internal mesh. It's now going to look like a giant cube again. And I don't like that this is a giant cube, because this isn't very easy to read. So what I'm going to do instead is I'm going to cut it. Give this thing a little clip in the Y direction. This is like kind of, you can see the red line. Give this little clip a thing, and it will show the velocity of the air. It's on the other side. Here we go. Looks like it's cut it here. Let me go into 2D viewing so I can zoom into the points that I care about. So you can see the, this is again for velocity. The velocity is a lot, whoops, I don't mean to be doing that. Let me click off of that, there we go. Velocity is slower near the surface, but you'll see an increase in velocity right at that peak of the mountain, because that's all that air that's coming down this way is then hitting, the peak of the mountain and growing really fast right there. Because again, there's low pressure at that point and high velocity, they work together in that way, where the high velocity and the low pressure combine, and the velocity right on top of that mountain is very fast. If you're standing up on top of this little plateau, you'll expect very fast wind conditions coming from whatever wind is coming from over here. And then after this, in these little valleys, you'll see that the wind conditions are very low, especially like right after this little rut here. There's low wind, low wind. There's low wind up here, but there's higher wind right on the peak of this. And that makes sense because all of this low wind, even though it's slow, when it hits that, it starts to speed up again because, again, it's all being compressed into this small thing. And the speed just increases. If I just switch this over to pressure, oh, that doesn't work. I have to actually go into clip 1 and I have to switch it to pressure. You'll see, there we go, that's exactly what I expected. Right on that same dot where the velocity is super, let me click off of that, I don't want to change the thing. Right on that same dot where the velocity was super high, you can see the pressure is a little bit lower there. Lower pressure here, lower pressure here. Somewhere on this map, there is a point where the pressure is negative. That's an extreme number. Where is that? There's a point on this somewhere where the pressure is very low. Let's switch back to 3D viewing so I can rotate this. Okay, I can kind of see where that would be. Right along that ridge. It's white for me. I wonder if there's a ridge further back. There is a sharper ridge. If I take the clip and I were to click it right here, drag it forwards a bit, might be able to apply that, right? It's going to take a little bit to load, but yeah, you can see some of that the harsher colors right on into that mountain. Oh, there's the blue right there. That's the super low pressure. That's at like, negative 190 versus everywhere else, which is like, wait, is that 190? 19, yeah, 190. 190 here, and then, the most high pressure you get is around only 46. Doesn't get too high, but apparently right here on the top of that sharp mountain ridge, it gets really high pressure. Anyways, I think it's very interesting, and of course I've given you all the files so you can play around with all this, play around with checking all of the details. You can even see, hold on, I forgot to even mention that the mesh is important. You can see how different the mesh quality is around the terrain here. Around the terrain, the mesh is very strong. Top of the plateau seems a bit flat, so it seems to be less meshed. And the box mesh, the actual like terrain box mesh is very, very simple. I didn't give it too much detail, but I wanted it to look kind of natural-ish when it joined up with this terrain. So the terrain here, you can see the mesh is very complex, very sharp, sharper than, again, like I showed earlier, sharper than the actual input file, which was very boring looking. If you zoom in a bit, oh, here we go. Yeah, you can see this is a very high quality. So even if you have high quality terrain, you're worried, oh no, it might not work the same. This is pretty high quality. I don't think you can really miss out on quality when it comes to this. But that should be all for this tutorial. If you just feel free to check out all of the files that I've sent in. I'm going to send like pictures of the results, and I'm going to send all of the different variations of the input files. I'm going to do the pre-mesh, post-mesh, and post-processing files, so you can see after each step what it will look like. I'm going to share a little document explaining the instructions of how to run it, or actually I'll put that in the description. The description itself will show the steps of what commands you should use, like in what order and what they all do. But yeah, that should be everything for this tutorial. I hope you have enjoyed, and feel free, if you have any questions, ask them in the comments, because I might be able to answer them there too, if I'm still, kicking and checking in on the comments whenever you may ask these. But I hope you've enjoyed, and yeah, that was that.